You're standing at the edge of a commercial port watching a container ship ease slowly toward the dock. It's enormous, the kind of vessel that makes the tugboats guiding it look like toys. And just as the bow drops below your sight line into the water, you catch something that doesn't look right. A rounded bulge of steel pressing forward beneath the waterline. Blunt, heavy, completely exposed. On a machine engineered down to the last rivet for efficiency, it looks like someone made a mistake and nobody caught it before the ship left the yard. Every instinct says that shape creates drag, that it should slow the vessel down, that it doesn't belong there. Naval engineers looked at exactly the same shape and reached the exact opposite conclusion. This is the bulbous bow. And understanding why it works means rethinking everything you thought you knew about how a ship and the ocean actually negotiate. The ocean does not move out of the way for a ship. That sounds obvious until you think about what it actually means at scale. When a hull pushes forward through water, it doesn't slice through empty space. It displaces mass, enormous, continuous, relentless volumes of water that have nowhere to go, except outward and upward. The result is a bow wave, a crest of water that builds at the front of the vessel and travels with it wherever it goes. For the entire length of the journey, it represents energy. Specifically, it represents energy that the engine generated, that the propeller transferred to the hull, and that the water then claimed for itself instead of converting into forward motion. Every meter the ship travels, the bow wave is taxing it. For centuries, the answer was the sharp prow. The logic was clean and intuitive. If a hull cuts through water rather than pushing it aside in bulk, the bow wave stays smaller, the energy loss stays manageable, and the ship moves more efficiently. A blade meets less resistance than a blunt surface. That principle worked well enough for wooden sailing ships, for early steamers, for most of maritime history. Sharpen the entry angle, reduce the cross-section the water sees, and resistance drops with it. Simple, mechanical, effective. Then ships got bigger, much bigger. And at a certain scale, the geometry of cutting simply stops being the dominant variable. A sharp prow on a vessel displacing 200,000 tons is still a cutting tool, but the hull behind it is a moving wall, a wall pushing an almost incomprehensible mass of seawater aside with every forward meter. The water the prow cleanly parts immediately encounters the full width of the hull and has to go somewhere. At that size and at the speeds these vessels maintain across ocean crossings, the bow wave does not stay small because the prow is sharp. It builds anyway. It builds because the physics of that much displaced water at that much speed simply overwhelms the geometry. The sharp prow had reached its limit. The bow wave was still there, still taxing the engine, still bleeding energy away from forward motion on every voyage. What the industry needed was not a sharper blade. It needed a completely different way of thinking about the problem. The insight that changed everything didn't come from making the hull more aggressive. It came from understanding what a wave actually is. A wave is not a physical object moving through water. It is a pattern of pressure, energy traveling through a medium. Pressure patterns have a property that solid objects don't. They can interact. When two wave systems meet in the same space at the same time, they don't collide, they combine. Depending on how their timing lines up, that combination can go one of two ways. If the crest of one wave meets the crest of another, they amplify. The resulting wave is larger, more energetic, more disruptive. But if the crest of one wave meets the trough of another, something different happens. They cancel. The energy doesn't disappear, but it redistributes across a dramatically flatter pressure field. The technical term is destructive interference. It is the same principle that makes noise-canceling headphones work. A second sound wave introduced at precisely the right phase to neutralize the first one, not by blocking it, but by meeting it. The bulbous bow applies that principle underwater and at industrial scale. The bulb sits ahead of the main hull below the waterline. As the ship moves forward, the bulb displaces water and generates its own pressure wave. That wave is not accidental. The bulb is shaped, sized, and positioned so that the wave it produces travels forward and meets the ship's natural bow wave at almost exactly the wrong moment, which is to say at precisely the right moment for cancellation. Crest meets trough. The two systems partially neutralize each other. The enormous pressure wall that the bow wave represents is flattened. Energy that would have been lost to the water is instead redistributed in a way the hull can work with. What this means in practical terms is that the ship moves through a pressure field that has already been partially pre-shaped before the main hull arrives. The water ahead isn't waiting to be pushed aside in bulk. It has already been negotiated with. The bow wave is already being dismantled by the time the hull reaches it. The bulb is not contributing thrust. It is not making the engine more powerful. It is doing something more useful than that. It is removing one of the largest continuous forces working against inch forward motion using nothing but geometry, positioning, and physics. The physics is elegant. The numbers make it impossible to ignore. A well-designed bulbous bow reduces hydrodynamic resistance enough to cut fuel consumption by up to 15% at cruising speed. On a vessel burning hundreds of tons of heavy fuel oil per day across a 2-week Pacific crossing, 15% is not a marginal efficiency gain. It is millions of dollars per vessel per year. Multiplied across a global fleet of thousands of container ships and tankers making continuous ocean crossings, the cumulative fuel saved and emissions avoided because of a rounded lump of steel below the waterline is genuinely difficult to overstate. But the bulbous bow is not a universal solution. And this is the part that separates the engineering from the marketing. The cancellation only works correctly under specific conditions. Naval architects use a measurement called the Froude number, a ratio that describes the relationship between a vessel's speed and the length of its waterline. For destructive interference to function as intended, the wave the bulb generates must arrive at the bow wave at precisely the correct phase. That timing is determined entirely by the Froude number. Get it right and the waves cancel. Get it wrong and they compound. The bulb that saves 15% in fuel at the correct speed and hull length becomes additional drag at the wrong ratio. It makes the ship less efficient, not more. This is why bulbous bows are not fitted to every vessel in the water. A small fishing boat operates at speeds and hull lengths where the wave timing is completely misaligned. A coastal ferry, a river barge, a leisure craft, none of them sit inside the Froude window where the geometry produces cancellation rather than amplification. Fitting a bulb to those hulls would be counterproductive. The solution is powerful, but it is also precision. It works extraordinarily well inside a specific operating envelope, and it stops working the moment that envelope is exceeded. The ocean doesn't reward approximation. The numbers have to be right, or the wave wins. Step back from the mechanics for a moment and look at what the bulbous bow actually represents as an idea. The sharp prow was a philosophy. It said that the way to deal with resistance is to meet it directly and overpower it. Cut harder, sharpen the angle, force the water aside. It is an aggressive approach, and for most of maritime history, it was the correct one. The bulbous bow represents a completely different way of thinking. It does not fight the bow wave. It introduces a second wave system designed to make the first one disappear. Where the sharp prow said, "push harder," the bulb says, "pre-shape the problem before it becomes one." The practical result is something that sounds almost paradoxical. A 200,000-ton vessel crossing an ocean behaves hydrodynamically. as though it is longer and more streamlined than it physically is. The water ahead of the hull has already been worked on by the bulb's pressure field before the main hull arrives. The ship is not overpowering the sea. It is, in a very precise sense, tricking it, presenting a hydrodynamic profile that the physics of wave resistance would normally require a much longer and more slender hull to achieve. This philosophy shows up elsewhere in engineering whenever brute force hits a physical ceiling. Aircraft winglets that redirect wingtip vortices rather than fighting induced drag directly. Riblet surface textures on competitive swimsuits that reorganize boundary layer flow, instead of simply reducing friction. In each case, the solution stopped trying to overpower the physical force and started working with the underlying mechanics of how that force behaves. The bulbous bow belongs in that category. It is one of the cleanest examples in the industrial world of counterintuitive design outperforming the obvious answer. The ugly shape at the front of the ship is not fighting the ocean. It is thinking ahead of it. The concept was not invented by the container shipping industry. The theoretical groundwork was laid in the early 20th century, with experimental applications appearing first on naval warships where fuel range and speed were existential priorities. But commercial shipping was slow to adopt it. For decades, the efficiency gains were understood, but the economic pressure to act on them wasn't strong enough to force a redesign of an entire global fleet. Then the 1970s fuel crises hit. Fuel prices spiked hard, and suddenly the operating economics of ocean freight were rewritten overnight. A 15% reduction in fuel consumption stopped being an interesting engineering footnote and became an urgent financial necessity. Bulbous bows moved from experimental to standard fitment across commercial shipping within a generation. Today, virtually every large cargo ship, tanker, and container vessel is built with one. But the design hasn't stopped evolving. Modern bulb geometries are computer-optimized for specific routes, speeds, and cargo loads using computational fluid dynamics tools that simply didn't exist when the first commercial bulbs were fitted. Some next-generation designs are exploring variable and retractable bulb configurations, allowing the geometry to shift and stay inside the optimal Froude window as operating conditions change. The shape is old. The thinking behind it keeps getting sharper. Next time you see a container ship at port, in footage, on a live vessel tracker, look just below the waterline at the bow. That round protrusion is not a flaw. It is not an afterthought. It is a deliberate act of physics, a piece of geometry placed with precision to make a wave disappear before it can steal energy from a machine that burns millions of dollars of fuel crossing a single ocean. A 200,000-ton vessel that doesn't overpower the water, it negotiates with it. The ugliest part of the ship is doing the most elegant work.